This is part one of the series Relationships Within Triangles, and just as the title says, we're going to be looking at the relationships between angles and sides of various types of triangles and within triangles. So to start off the series, let's look at perpendicular bisectors. Now we know that a bisector is something that cuts something into two congruent pieces, that is, two pieces that are equal in measure or length. And so the theorem says, in a plane, if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So over here we have point C that is on the perpendicular bisector of segment AB. So according to the theorem, this point must be the same distance from point A as it is from point B. So to look at these details, let's draw a picture. Let's draw those two lines in. And we can see now we have two triangles. We have triangle AQC and triangle BQC. Now, because this is a right angle, this must be a right angle, and these two sides are congruent to each other. Therefore, we know that CQ is congruent to itself by the reflexive property, and so triangle AQC is congruent to triangle BQC by side angle side. Side angle side. So we know that congruent parts of congruent triangles are congruent, so AC must be congruent to CB, and therefore proving this perpendicular bisector theorem that if a point is on the perpendicular bisector, it's equidistant from the endpoints. Now, equidistant, of course, means a point that is the same distance from any two or more objects. So this point is equidistant from these 2 points because it's the same distance from here to here. Just as Q is equidistant from the endpoints. QA and QB are congruent, so it is equidistant from those endpoints. Let's take a look at the converse of the perpendicular bisector theorem and see how that one plays out. The converse says, in a plane, if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of the segment. So first we said a point lied on the perpendicular bisector. Now we're saying the point is equidistant from the endpoints, therefore it must be on the perpendicular bisector. So to show this theorem, I've drawn a line, a segment between C and Q, and I've made point Q the midpoint of segment AB. So that means because this is equidistant from the endpoints, we know these two are congruent, and because this is the midpoint, it's equidistant from these 2 points. So AQ and QB are congruent. We also know that CQ is congruent to itself by the reflexive property again. So triangle AQC is congruent to BQC, this time by side, side, side. Side, side, side. And therefore, since these two triangles are congruent, these two angles must be congruent. Since those two angles form a linear pair, and they're congruent, we know that linear pairs are supplementary, so they add up to 180 degrees. So this angle and this angle have to be 90 degrees apiece. Therefore, CQ is perpendicular to AB, and since CQ passes through the midpoint of AB, it is the perpendicular bisector of AB. So that proves out this theorem. Now, of course, these proofs were very informal proofs, but if you want to go through the formal proof of that, it shouldn't be too difficult. So let's go ahead and work some examples and see if we can't solidify this concept a little bit. In this first example, we have line BD is the perpendicular bisector of segment AC. Therefore, by the perpendicular bisector theorem, point D must lie on the perpendicular bisector and it must be equidistant from these endpoints. So if AD is 27, then by the theorem, CD must be 27. So that was a pretty straightforward one. Let's take a look at this next one. we have QS. Line QS is perpendicular to PR. You can see that point S is equidistant from points P and R. That means that it must lie on the perpendicular bisector of this segment by the converse of perpendicular bisector theorem. Therefore, any point on this perpendicular bisector has to be equidistant from the endpoints. Since PQ is 5, QR must be 5, and that makes PR equal to 10. Okay, now let's go on to the next example down here. And here we have a very similar example. We have HF, line HF is the perpendicular bisector of EG. Therefore, H is equidistant from endpoints E and G. So that makes HE congruent to HG. Since HE is congruent to HG, we know that 2x equals 3x minus 8. Now when we play out the algebra here, if you want to work with negatives, that's fine. I don't like working with negatives, so I'm just going to subtract the 2x from this side. So 0 equals x minus 8. Let's add the 8. 8 equals x. Now we weren't looking for x. We're looking for the length of segment HG. HG is given by 3x minus 8. So we're going to substitute this into that expression. So 3 times 8 minus 8. Well, 3 times 8 is 24. Minus 8 is 16. Now, these were just a few basic examples, but hopefully you get the idea. So let's move on to the next section and see what we have. Here we're working with angle bisectors. And the angle bisector theorem says if a point lies on the bisector of an angle, then it is equidistant from the two sides of the angle. In this picture, we have ray BD is the bisector of angle ABC, and we know that by these two congruent angle symbols. And so the whole goal here is to prove that DA is congruent to DC. DC and DA represent the distance from that point to that side and this side, because the distance from a point to a line is the length of the perpendicular segment from the point to the line. So let's see if we can show that these two triangles are congruent. Well, we know that these two angles are congruent because they're right angles, and these two angles are congruent because that's given to us. BD, segment BD, is congruent to itself because of the reflexive property, so we have a case of angle, angle, side, angle, angle, side. So yes, in fact, these two triangles are congruent, and therefore AD is congruent to DC, which proves out this theorem that the point is equidistant from the sides of the triangle, that this point is the same distance from C as it is from A. So that's the angle bisector theorem. Pretty straightforward theorem. Look at the converse of the angle bisector theorem. If a point is equidistant from the two sides of an angle, then it lies in the bisector of the angle. So in this case, we do not know yet that BD, ray BD, is the bisector of angle ABC. So we're going to try and show that these two angles are congruent. Well, we're given that this is perpendicular to this. This represents the distance because it says point D is equidistant from A and C. We know these two sides are congruent. And so we know that BD is congruent to itself by the reflexive property. Hopefully you can see that triangle BCD and BAD are right triangles, and BD is the hypotenuse of both of those right triangles. So we have a case here of hypotenuse-leg theorem. So these two triangles are congruent by hypotenuse-leg, and by CPC-TC then this angle ABD, is congruent to angle CBD. And so that proves out the the converse of the angle bisector theorem. So just as a quick recap, if a point is on the angle bisector, then it is equidistant from the sides of the angle. If a point is equidistant from the sides, then it is on the angle bisector. So we know that this cuts this angle into two equal pieces. So let's go ahead and see if we can't work some examples for this couple of theorems. In this example, we're looking for angle GFJ. So here we see that point J is equidistant from the sides. Therefore, by the converse of the angle bisector theorem, we know this is a bisector of angle GFH. So if this is 42, then we know that angle has to be 42 degrees. The next example is not much more difficult. We see that SQ, ray QS, is the bisector of PQR. Therefore, this point is equidistant from the sides of the angle. So we know that 5x equals 6x minus 5. And so doing some quick algebra here, 0 equals x minus 5. 5 equals x. So if x equals 5, we're looking for segment RS. So we're going to substitute that in there. So 6 times 5 minus 5 is 30 minus 5, which is 25. All right, let's take a look at another example. In this example, we have point D equidistant from the sides of angle ABC. This and this are the same. So we know this is an angle bisector. So that must mean that angle ABD is 56. So the measure of angle ABD is 56 degrees. That means that angle ABC is 56 plus 56, which is 112 degrees. Again, these aren't intended to be difficult examples. They're just exemplifying the two theorems. So the last one, we can see that this ray, KM, is the bisector of angle JKL, and so point M is equidistant from the sides. So we know that 4x equals 2x plus 12. Let's subtract the 2x. 2x equals 12. X equals 6. We're looking for JM, so 4 times 6 is 24. And hopefully you've got a handle on these bisector theorems. So we've covered perpendicular bisector, converse of the perpendicular bisector theorem, angle bisector theorem, and the converse of the angle bisector theorem. So let's move on to the next section and see what we have there.